Good morning. Let us continue the lesson. I decided to go one or two more sessions on what we have learned so far before actually moving to the new topic. That would be mathematical logic. But before doing that, let me complete my discussion about what we have learned so far, and that was mainly the notion of a metric. So what was a metric? So we have an abstract set, so let me call it X. And then we multiply this set by itself, the Cartesian product. And then I have a function d from this Cartesian product to the set of real numbers with four properties. Yes, so the first property is that for all x and y in the set X, the output of dx and y should be non-negative. For all x and y in X, dx and y is equal to 0 if and only if x is equal to y. For all x and y in X, d of x and y is equal to d of y and x. That's the symmetry property. And mainly the last one, which is usually problematic to show, is that for every triple of x, y, and z in the set X, dx and z, the distance from x to z, is less than or equal to distance from x to y plus the distance from y to z. But the examples of a metric so far that I introduced, one of them, of course, was the Euclidean metric on the set R. So if you remember, we had this metric D from R times R to R itself, and this is the natural distance metric that we have on R, and that is just simply the absolute value of x minus y. So this means that if this is the real line and I have 2 points with coordinates x and y on the real line, if I want to find this distance is actually absolute value of x minus y. And we also talked about another metric on the same set R, and that was called the discrete metric, and then we defined it in that way. We said that this becomes 1 if x is equal to y, if x is not equal to y, and 0 if x is equal to y. But that's also defining a metric. We also showed that these two really define a metric. But today let me go to one dimension higher. So this time, so here in these two cases, you see here I am taking x to be r. But now let me take this x to be r squared, yes? So what is r squared? This means the Cartesian product of r by itself, actually. So this means the set consisting of all ordered pairs a and b, such that the first component belongs to r and the second component also belongs to r. So this symbol that I have used here means and. Now I want to define a metric on this r squared. So how can I visualize r squared? That's clear. You just visualize it as the normal coordinate system, yes? So if you have these x and y axis, then this is what we imagine for r squared. So that is what we imagine for it. But abstractly speaking, r squared is this one. Now I want to define the usual metric, the metric that we learn by looking around us. That is what is called Euclidean metric. So what does it mean? It means that I want to define a metric so that it is capable of giving me the distance between 2 points A and B on the coordinate plane. So I give you these 2 points and I want to measure the distance between them. Of course, this is something that you know from very early courses, even in high school. So if I want to measure the distance, I would say that, okay, I define a metric D from Cartesian product of x by itself, but here x is r squared, Cartesian product by r squared to the set of real numbers r, so that D, the distance between A and B, is equal the most natural distance. That is the difference between x coordinates of these points squared plus the difference between y coordinates of these points squared, and then we take the square root. Okay, so that is exactly the formula for the distance in the plane. So I give you 2 points, x and b, A and b, and I ask you to calculate the distance. This is the formula. This is the difference between x coordinates of point A and B, and this is the difference between y coordinates in A and B. Of course, because we extracted the axioms, the properties of a metric by the distance formula that we are familiar with in this universe, it is not surprising that d indeed is actually a metric. Yes? But of course, mathematically speaking, you need to prove that this is a metric. Okay, so how should I prove this? Let us, for example, try to go through it one by one. So the first thing is I need to check that the output of my metric is a non-negative number, but that's very clear. So for every pair of points A and B that I give you on r squared, the output is non-negative. Why is that? Because this second power is non-negative. This is also non-negative. So when I add them, it becomes non-negative. When I take square root, that's also non-negative. So the first actually one is clear. What about this one? Is it true? We have to check. So I need to ask myself, is it true that for any pair of points A and B, if distance between A and B is 0, this happens if and only if A is equal to B? Okay, so first let us check in this direction. If someone tells me that the points A and B are the same, can I conclude that the distance between them are the same? Is the same? The answer is yes. So if the distance between them is 0, the answer is yes. Why? Because if the points are the same, it means that the x-coordinates are the same, so the difference is 0, and the y-coordinates are also the same, so the difference is 0, so yes. The whole function d of a and b is equal to 0, and I am done. But what about the other way around? So assume that someone tells me that the distance between 2 points a and b is equal to 0. What can I conclude? I can conclude that the square root of x sub a minus x sub b squared plus y sub a minus y sub b squared is equal to 0. Of course, I can get rid of a square root sign by raising both sides to power 2. So let me raise both sides to power 2. I get this one. But can I conclude that each one of them is individually equal to 0? In this case, the answer is yes. Why is that? Because this is a non-negative number because of the even power 2, and this is a non-negative number because of the same reason. And now I know that the sum of two non-negative numbers is supposed to be 0. This cannot happen unless each one of them is individually equal to 0. So this means that this should be 0 and this should be 0. Okay, but what does this mean then? That this means that x of a is equal to x of b and y of a is equal to y of b. This means that I have 2 points, the x coordinates match, the y coordinates match, so it means that the points are actually the same points. Okay, and the symmetry argument is actually clear here. So why do you think for every pair d of a and b should be equal to db of a, b and a? The reason is clear because, for example, if I interchange a and b in this formula, then this becomes x of b, this becomes x of a, so this means these two will be interchanged. The same happens here. But when these two are interchanged, because that's a minus sign, it means that I will pick up an overall minus sign, but that overall minus sign will be eliminated because of the even power. So nothing changes. So this is indeed true. So the only problematic one is to check if the triangle inequality is true. Of course, we are more or less, we're certain about that this is true. For example, if you were a physicist, you really don't bother to check the triangle inequality because you said to yourself, okay, I took the notion of distance, I took the notion of metric from actually the distance formula in the universe around me, so, and I abstract the notion of metric out of it, so this means that, okay, definitely this is indeed a metric. But for a mathematician, it is better, we have to check it out. Okay, so how should I check it out? I need to convince myself that if someone gives me an arbitrary triple of points in the set r squared, I need to convince myself that the distance from A to C is less than or equal to the distance from A to B plus the distance from B to C. Okay, so we have to check that. Okay, so let me rewrite these as the formula, the distance formula. So what happens for the left hand side, I will have square root of x sub a minus x sub c to the power of 2 plus a y of a minus y of c to the power of 2, and then I will have less than or equal. I will do the same thing here. So I will have x of a minus x of b squared plus y of a minus y of b squared, and then I will have plus square root of xb minus xc squared plus yb minus yc squared. So I need to convince myself that this is true independent of which triple of points I choose in the plane. Okay, so there are many ways that we can prove inequalities. One way is to start simplifying the inequality in a reversible manner. So we have to check out every step that I go forward, it is also reversible, so I can come back. So I do this step by step until I reach to an inequality whose truth is obvious to me, and I can conclude the last inequality is true. And if I have respected to follow everything reversibly, it means that the original inequality is indeed equivalent to the final inequality, and I have shown that the original inequality is also true. So this is a little bit technical. So if I want to start simplifying this, the first thing comes to mind is to get rid of the square root signs. And then if I want to get rid of the square root sign, one general strategy is to raise these things to power 2. Okay, the left hand side I will not have big problems, because when I square it, this square root sign is cancelled, it's good. But on the right hand side, I cannot just simply remove the square root sign, because this becomes the first one squared. Yes, the square root sign is removed. The second one is squared, the square root sign is removed. But 2 times the first one times the second one becomes a little bit lengthy expression with the still square root sign left. Okay, but this is how it is. We have to live with it. So either we have to work with what you see here in front of you, or you can introduce a little bit of notation to write this expression compactly, more compactly, so that the algebra becomes simpler. Okay, so what we want to do, let me introduce something here. So you need to be also a little bit clever here, so that you can find the shortest way to do it. Okay, so what we do, I want to introduce some labels. I would say that, for example, let me introduce alpha to be absolute value of x sub a minus x sub b. Yes, and then I introduce beta to be absolute value of y sub a minus y sub b, and gamma to be absolute value of x sub b minus x sub c. Finally, theta, I introduce it to be absolute value of yb minus yc. Okay, and by the way, I hope that you agree with me, it doesn't matter if I put absolute value here or power of 2, because if I have absolute value of a number squared, it doesn't there is no difference between this and this one squared itself. But here I prefer to put absolute value. So if you don't mind, let me just do it right away. So I put all of them to be absolute value. There is no difference between them, okay? Because 2 is an even number. Okay, but one more thing I want you to know is that what can I write for this expression? So absolute value of x sub a minus x sub c can be written as absolute value of x sub a minus x sub b plus x sub b minus x of absolute value of x sub c. Yes, I have done nothing. I have taken this away, but I have added, because if I take this away, I will have the same thing. But if you remember, we had something in the previous lecture that if I have absolute value of, say, a number m plus n, this absolute value is less than or equal to the absolute value of the first one plus the absolute value of the second one. This is one of the most important inequalities in mathematics. I really recommend you to remember that. Okay, so now I can give the role of m to this, and I can give the role of n to this. Okay, and then what can I do? I can write that this is less than or equal to the absolute value of m, which is absolute value of x sub a minus x sub b, plus the absolute value of x sub b minus x sub c. But if I ask you now, what is this? Do you remember? I called this one to be alpha, and I called this one to be gamma. Yes? So then it becomes less than or equal to alpha plus gamma. So I was able to show that this expression is less than or equal to this expression. So if I raise both sides to power 2, I will get x sub a minus x sub c squared is less than or equal to alpha plus beta squared. So let us keep it here. Okay? But similarly, I don't want to go through the calculations. I can write something for this. So I can prove that absolute value of y sub a minus y sub c squared is less than or equal to, oh, so I made a mistake here. This is not beta. This is gamma, yes? And then this becomes less than or equal to beta plus theta squared. Okay? This is something similar. This can be done similarly, yes? Okay, now if you look at this inequality, the left-hand side of this inequality, so let me write the left-hand side, which is equal to this one. The first component, the first term is less than or equal to this, and the second term is less than or equal to this. So hopefully you agree with me that the total left-hand side is less than or equal to alpha plus gamma squared plus beta plus theta squared. Yes, this I know. And the right-hand side of the inequality, I mean this expression, using this alpha, beta, gamma, and theta that I introduced, is equal to square root of, oh, that's too big, square root of alpha squared plus beta squared, and then plus square root of gamma squared plus theta squared. My goal is to show that the left-hand side is less than or equal to the right-hand side. But I hope that you agree with me that instead of showing the left-hand side is smaller than the right-hand side, if I succeed to show this one is less than the left-hand side, is less than the right-hand side, then I am done. Yes, the left-hand side is less than or equal to this expression. If I manage to show that this expression is less than or equal to this expression, then I am done. So from now on, I focus my energy to answer this question, okay? Is it the case that square root of alpha plus gamma squared plus beta plus theta squared is less than or equal to square root of alpha squared plus beta squared plus square root of gamma squared plus theta squared? Yes, is that possible to prove it? Okay, now I momentarily forget about my original inequality and focus on this new inequality. Okay, and I want to simplify this inequality in a recursive way so that I come up with a trivial, which is always true inequality. Okay, so we raise both sides to power 2. What happens? This becomes alpha plus gamma squared plus beta plus theta squared. And on the right hand side, I will have the first one squared, which is this one, the second one squared, which is this one, but of course plus 2 times the first one times the second one, which is alpha squared plus beta squared times gamma squared plus theta squared. And then you see that on the left hand side, by the way, this is recursive, yes? Why? First of all, this is clear that I can go in this direction, but because all of these expressions that you see are non-negative, I can go back by taking a square root sign and factorizing it in this, factorizing the right hand side in this form. So this is indeed recursive. Now I go forward and I square the left hand side. I expand the left hand side. Alpha squared to alpha gamma plus gamma squared plus beta squared plus 2 beta theta and then plus theta squared is less than or equal to alpha squared plus beta squared plus gamma squared plus theta squared plus the rest of the terms. Yes? But now you see that something happens here. Alpha squared and alpha squared are gone. Beta squared, gamma squared are all gone. By the way, I forgot to mention that this is also reversible. Yes? So I can collect these terms. I can collect these terms back. But now you see that I have a 2 here and I have a 2 here. Oh, by the way, I forgot. This is also simplified. So theta squared is also simplified. And then you see that I have a 2 here, a 2 here, and a 2 here. I divide everything by 2. So what I get is this expression. So this becomes, let me write it here. So alpha, this becomes alpha gamma plus beta theta is less than or equal square root of alpha squared plus beta squared times gamma squared plus theta squared. Yes? And this is also reversible, so it's very simple that this is reversible. But now what I do, I want to raise both sides to power 2 because still it is not clear to me if this inequality is true, even though this inequality is simpler in form than the original inequality, but I really don't know if this is still the trivial one. Okay, so it is not clear yet. So I have to continue simplification with the hope that I can come up with a simple inequality. Okay, so if you don't mind, let me actually take this with me, if it is working, to the next page. Okay, and continue from there. Okay. But that was also done in a recursive way, yes? But then I raise both sides to power 2. Alpha gamma plus beta theta squared is less than or equal to alpha squared plus beta squared times gamma squared plus theta squared. So, but is this action reversible? This is something that you need to check. If I want to go backward, I need to take square root from both sides. Okay, for the right hand side, of course I am getting back, no problems. But for the left side, I will go to absolute value of alpha, gamma plus beta, theta. But this is not absolute value 1. This is the same expression without absolute value 1. Can I really remove that? If the answer is not yes, it means that this last step is not reversible. But fortunately, it is possible. Why? Because if I go back to the definition of my alpha, beta, gamma, and theta, I realize that all of them are non-negative. Why is that? Let us go back. Alpha, beta, gamma, and theta are the outputs of absolute value. So alpha is non-negative, beta is also non-negative, and etc., etc. So this means that this expression is non-negative. So yes, this step is also reversible. Okay, then what I do? Still, is it clear that this is true? Not yet. So I need to continue my simplification. So the first one squared 2 times the first one times the second one plus the second one squared is less than or equal. I expand the right hand side, alpha squared, gamma squared, alpha squared, theta squared, beta squared, gamma squared, and then I have beta squared, theta squared. And then let us see if I can simplify more. Yes, this one and that one are simplified. This one and that one is also simplified. And what is left on the left hand side is 2 alpha, gamma, beta, theta is less than or equal to alpha squared, theta squared plus beta squared, gamma squared. Is this reversible? Yes, because I just simply add these terms to both sides. But this is really simple now compared to the original one, but is it trivial? Is it guaranteed that this is true for any alpha, beta, and gamma, which are non-negative? The answer is yes, but you have to be a little bit observant because Here the trick is to move this to the other side, so the left hand side becomes 0, the right hand side becomes alpha squared theta squared minus 2 alpha gamma beta theta plus beta squared gamma squared. And this is also reversible, yes? But then I can write the right hand side in the form of a complete square, and that is alpha theta minus beta gamma. So if I ask you what is the expansion of that, you would say me this one is squared, which gives me the first one, 2 times the first one times the second one, which gives me this one, and the second one squared. That's correct. And now, is this true? 100% yes. So this is indeed true. Okay, why is that? Because this is an even power, so definitely the answer to this expression is non-negative. Okay, so and then because all of these steps are reversible, so you see that's a very, very crucial thing, that all the steps should be reversible, then it means that, okay, I can come back and say that, okay, this original inequality is true, and because this inequality is true, this means that the left-hand side, which is less than this, and this is less than that, the left-hand side is smaller than the right-hand side, so I am done. Okay, so the reason I really wanted to go through this, because I want you to see that I am not adding something to mathematical concepts here. This is just one single technical problem. We have the metric, by the way, this metric is called the Euclidean metric. So let me write the name here, so Euclidean metric in 2 dimensions, of course. So it is not adding something to our mathematical concepts, that's the same notion, but I had to solve this technical problem, which is also another phase of mathematics, so you have to be very good at it if you want to continue any career in mathematics, yes? Okay, so I think that's a good point here to stop. I hope that you enjoyed the video. Until the next video, be safe and goodbye. Thank you.